right. Go ahead and get started here. Hello, everybody. This is Mike. Yeah, so this is my first live stream. See if anybody goes ahead and hops on and watches, but for now, we'll just go ahead and get started. I'll explain what we're going to do here. This is going to be unscripted, so a little different than probably what you're used to seeing as far as my content goes, so that should be interesting. But what we're going to do is we're going to open up Logisim, and I don't know if any of you have seen Ben-Eater's videos about computer hardware and low-level programming and all that. I'd highly recommend checking him out if you haven't seen those. They're great. In fact, they kind of inspired me to start this channel and do a lot of things that I'm doing now. But one of the things that he did was he built an entire 8-bit CPU completely on breadboards, which was really cool to watch. So what we're going to do is we're actually going to go into Logisim and we're going to build kind of our own version of that CPU, but with a little bit of a twist. We're going to build that CPU entirely out of NAND gates, because it turns out that NAND gates, you can build any, you can use NAND gates to build any other logic gate you want. So I figured that'd be kind of a fun little challenge for us to do here. And we'll probably, I've got some ideas to make some improvements to Ben-Eater's design too, primarily in the number of registers we need. I think there's some ways to reduce the number of registers we need by a little bit, and also to get the instructions to execute a little bit more quickly. A lot of the instructions in Ben-Eater's CPU, they required quite a few clock cycles to execute, and I'm pretty sure we can get that down to just 2 clock cycles for every instruction. So we'll see if we can do that here. But we'll go ahead and go into Logisim. Let me zoom in here. Okay. So we're going to pull an AND gate in here. I'm actually going to make this a narrow profile instead of the medium profile. I just kind of like how these ones look a little better. Connect some inputs here. Okay, so yeah, we've got an AND gate. Pretty simple. Output's 1 unless both of the inputs are 1, or if in the case of like maybe a 3-input NAND gate, we'd have to have all 3 of the inputs be 1 in order for the output to turn off. And yeah, if we can make all of the other types of logic gates with these gates as well. For example, if we just take some NOT gates and invert the inputs, then we can turn our NAND gate into an OR gate, which we can see here. And then we could use inverters on the output to change the OR gate into a NOR gate, or even our NAND gate into a NAND gate. And we can use a couple of, or a few different NAND gates in the right configuration to make exclusive OR gates, and you can use those to build things like adders and yeah. So I think the first thing we're probably going to do here, as far as building our actual hardware, is I think I want to start by building the RAM. We're going to have 16 bytes of RAM. We're just going to build the RAM out of some D latches, which are pretty easy to build out of NAND gates. It turns out I did a video where I showed how to do that, so I won't necessarily go into a lot of detail here about that, but we'll just kind of pop a couple of NAND gates here and build our D latch. see if I can get this going right. Doesn't look like anybody's on the stream yet, but if anybody's watching and I'm just not able to see that, then go ahead and let me know if the audio quality isn't good, because I can't really hear that on my end. Maybe, yeah, let's see. Test, 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 test. Okay, yeah, cool. I just tested it by plugging some headphones into my phone and listening to the audio, and it seems to be working okay. But yeah. Oh, I actually made a little bit of a mistake here. Whoops. Okay, let's disconnect those. There we go. We have our input enable, and we have our data input. Okay, so got a D latch. Pretty simple. We can change our data input all we want, but the data won't get stored into the latch until we toggle the input enable. And then this isn't a synchronous latch; it's asynchronous. So the data stored in the latch will actually get read at any time that the data input is on. But that's fine for a RAM. We don't need a synchronous latch here, and that'll let us build this out of not as many logic gates as we would normally need. We'll just go ahead and copy and paste this a few times since we want to build an 8-bit machine. We'll need 8 bits for each RAM cell. So go ahead and do that. Connect all the input enables together. We'll go ahead and organize this just a little bit. Oh, and we have some oscillations. Go ahead and get rid of those. There we go. Okay, so now we have 1 byte of storage here. So what I'm going to do now is I'm just going to go ahead and organize all of our data inputs and use those to make a data bus. I'll just make things a little easier to stay organized moving forward. Yeah. On a lot of my videos, kind of the way I do these Logisim videos is I'll like write a script. I'll like write down everything that I want to say in the video, and then I'll do like a voice recording. Then I'll go in later and I'll do some screen captures of me actually like building all of the circuits that I'm describing in the videos, and that takes quite a long time usually. A lot longer than I typically show in those videos. So I think you guys are gonna get a little bit better of a picture of just how long it takes to do all this stuff here. There we go. Okay. Oh, come on. There we go. Okay, let's go ahead and start putting some labels on things. Oh, come on. Okay, label that for input enable. Okay. So we have some D latches, we have our data bus, we have a way to store data in this little RAM cell that we've got. But in order to make our RAM cell work the way we want it to, we need to have a way to put the value that's actually in this RAM cell onto the data bus so we can read it later. And the way I like to do that, is to use open collector NAND gates or open drain NAND gates. It depends on what kind of logic gates you're building. If you're building like TTL or DTL or anything using bipolar junction transistors, you're actually like building logic circuits. It's called open collector because you're using bipolar junction transistors, and that's one of the pins on those. But if you're using NMOS or anything like that that uses MOSFETs, then it'll be open drain because the drain terminal is what you're connecting the output to. But in order to kind of simulate that behavior in Logisim, we'll go ahead and go into here, and in output value, we'll go ahead and say 0 or floating, and that just means that anytime the gate output would normally output a 1, it just outputs a floating value instead, so it doesn't influence the state of whatever it's connected to. And that'll just help us communicate with the data bus without having any conflicts or anything like that. And to connect this to our RAM cell, let's go ahead and label this so we know what it is. I usually just like to throw a little OC on there just so I can tell that it's an open collector gate when I'm just looking at the schematic. So we'll go ahead and connect that to the inverted data pin of this little D latch here. And then we'll go ahead and copy this over a couple of times so we have 8 of them, because we need 1 for each bit in the cell. And we'll connect all of these up to an output enable. Give me a second while I do that. Okay, John Smith, are you building the whole computer in one stream? Yes, that's the goal. We're going to build the whole computer in one stream, and we're also going to build the entire thing out of NAND gates. I just figured that'd be a little fun twist on the project. So yeah, thank you for asking about that. Yeah, it might take a little bit, but I think it'll be doable in one session, because this is really a pretty simple architecture. Probably what's going to take the longest is just physically wiring everything together. That might take a bit, but I think we'll be okay. And just because this is going to bug me, I'm just going to swap around the order of these bus lines here, just because I usually like to keep the low bus lines on the right and at the top, just to make it easier for me to tell what's what while I'm connecting things together. But yeah, like I said at the beginning of the stream, this is all going to be based on Ben-Eater's CPU that he made on his channel, so I'd highly recommend checking that out if you've never seen that before. He did a really phenomenal job of building that CPU and explaining really everything that went into that. So I think he even has like kits that you can buy like online on his website if you want to like build one yourself. It comes with like all the breadboards and wires and all the logic chips that you need and stuff. I've never I haven't looked into purchasing one of those just because I like to build transistor based circuits just because I don't know, glutton for punishment, I guess. Yeah, it definitely takes a lot longer to do things that way, but it's a lot more satisfying, I find, to just build everything yourself. Yeah, I'm not like associated with Ben-Eater or anything, but yeah, he was definitely a big inspiration to me in me wanting to start up this channel and make a lot of the content that I do. see. Right. Let's go ahead and pull these down a little bit. We'll go ahead and pull our bus pins up, take those out of the way. And since we've got open collector outputs on our RAM cell, I'm going to go ahead and attach some pull-up resistors to our bus lines. That way they always get pulled high if nothing's outputting to the bus. And I'm also going to go ahead and make these input pins that are connected to the bus tri-state so that they can output floating values. So that'll be able to make our bus lines function the way they're supposed to. So I'll go ahead and just pull some resistors over here. We'll have them pull towards 1. And no, we want them east, not west. There we go. Now I'll go ahead and copy these a few times. We've got 8 of them, 1 for each bus line. There we go. Okay. So now let's just go ahead and verify that all this is working like it's supposed to. So we'll go ahead and toggle some of our input lines. Oh, what the? No, those are supposed to be inputs, not outputs. Whoops. Yeah, we want those to be inputs. There we go. Did I think I must have accidentally changed that instead of the pull behavior. No, 3-state. There we go. Yes, we want these to be 3-state inputs. We can make them float. So let's go ahead and turn these all floating so that they're not influencing the data bus. And then, yeah, let's go ahead and try and load something into our 1-bit RAM cell here, or 1-byte RAM cell here. Let's just go ahead and clear all these to 0. So we're forcing all the bus lines to 0. And then we'll just arbitrarily pick a number like 0, 1, 0, 0, 1, 0, 1, 0. And we'll go ahead and store that to our RAM. And now we'll turn all of our bus lines back to floating. Oh, come on. There we go. So now all of our bus lines are being driven by the resistors. And now if we do the output enable, we should see that 0, 1, 0, 0, 1, 0, 1, 0 get put back onto the data bus, so we can read it back into some other part of the machine later if we need to. Okay, so now that that's done, I think I'm probably going to need a little bit more room down here below the bus lines because there's some additional logic that's going to go into selecting the different RAM cells and such. Oh, what happened there? Oh, it just disconnected all my bus lines. That's fun. Okay, that's okay. We can just manually reconnect them here in a second. So, yeah. There we go. This will just take a moment. Yeah. Logisim is great. It's really powerful and really useful, but it does have a few little quirks like this that you just got to deal with while you're building stuff in it. There we go. Okay, and I think I'll probably also go ahead and pull these out just a little bit. Oh, it's not going to let me do it just a little bit, but that's okay. We can just move them back like that. Okay, so now we've got a little bit more room here to work with. So I think let's add an address decoder, like right up here in this space, just up above the RAM cell. And that's just going to be a NAND gate. We'll do a 5-input NAND gate because we want 4 address lines for 16 bytes. and one enable line because we want to control when the RAM is enabled and when it's not. So I'll go ahead and put a south-facing 5-input NAND gate here. Actually, let's go ahead and make this a 4-input NAND gate, I think, because we'll just connect this one to our address lines, and then we will have some other connections that will go to the read and write enables, and that'll be how we'll have the enabling behavior go down. Okay. I think I'm probably going to have to move these down a little bit to make room for the address lines. So we'll go ahead and do that just real quick. And of course that messed up our stored value. That's okay, because we don't actually need to worry about what's exactly stored here just yet. Go ahead and make my address lines right here. Have 4 of them. And we don't want these ones to be tri-state. Okay, so to make our address lines, we actually need the address here normally, and then we also need the inverted address in order to make our address decoder work properly. So I'll just go ahead and pull these over here. That'll be our address. And then I'll pull in some NOT gates, and that'll give us our inverted address. Just put the inverted address right here above the normal address. Connect all of these to some inputs. And it might be a little cleaner if I just pull it straight down there. There we go. Okay, so we have our address and we have our inverted address. Okay, and since this is the first RAM cell, this will be address 0. So we'll just go ahead and connect our address decoder to all of the inverted outputs, or inverted address lines, I mean. And that will make it so that this NAND gate will only turn off when we have address 0 on the address bus. So we'll just verify, yep. Okay. So when this gate outputs 0, let's pull a few more NAND gates over here. Have them also face south. Okay. And we'll just pull this down a little bit. Okay. So that'll be our read pin on our RAM. When this pin is 1, we'll go ahead and read the value that's on the bus into RAM. Oh, maybe not. Okay. Oh, and you know what? I just realized I said we were only going to use NAND gates, but we have some NOT gates here. But I think that's actually fine, because NOT gates are basically just 1-input NAND gates anyways, so I think we're good here. Oh, we got some more comments. Okay. Sorry guys, I can't be constantly looking at the comments. I am very new to this. Can you give me a step-by-step guide? How can I build my own 16-bit CPU? Can you give me resources? Yeah, so we're actually going to be building an entire 8-bit CPU in this stream, so you can either just follow along with this and kind of use that as your baseline, and you can just kind of make your 16-bit. It's pretty easy to make an 8-bit CPU into a 16-bit by just kind of doubling everything. And then the thing that this CPU is based on, actually, I mentioned earlier, but Ben-Eater, he made a whole series where he built this CPU on breadboards. So I'm just kind of basing this off of his work, except for I'm only using NAND gates because I thought that'd be fun. But yeah, look him up for sure. He's definitely a great place to get started with this kind of stuff. But hopefully you found that helpful. But yeah, welcome to stream. Thanks for joining us. Okay, so this is not working the way I expected it to, and I think what we're going to have to do is we're actually going to have to use an inverter here to invert this NAND signal. And like I said before, inverters are just one input NAND gates anyway, so it'll just make it a little cleaner than putting a whole NAND gate there, but it's basically the same thing. Okay, so I think we're going to have to do the same thing over here. So I'm going to have to invert this one. We'll just plop that down there. There we go. So now when I pop the read pin, we read the value in, and now we can copy this whole thing over here, over to the other side, and have that be our write signal, or read signal, I mean. Okay. Oh, and you know what? I just realized I mislabeled that one, so we'll... Oh, what just happened? There we go. Okay, we'll have that be write, and that one will be read. And we'll just go ahead and connect that over there. There we go. Okay. So now we have officially 1 byte of RAM that's working. So now we just need to copy that 16 times, or 15 times, I guess, because we have one already, so we don't need one of them. Okay, let's just see how we want to arrange this over here. Yeah, I think that should work pretty good. Let's go ahead and disconnect the address lines real quick because we don't want those just yet. We'll go ahead and wire the address lines up after we already have all 16 of our RAM cells. In fact, let me just go ahead and get these out of the way real quick, so that way we're not copying and pasting a bunch of garbage over while we're working. There we go. Okay, so now we can just grab all these, move these over here. Oh, whoops. Come on. If I can get it in the right spot there. There we go. Now we got 4 bytes. And once we've copied these over, we'll have 8 bytes. Oh, and apparently I didn't actually copy everything that I needed to. There we go. Now we've got 8 bytes. I'm going to zoom out a little bit so I can just grab everything at once. And now we should have 16 bytes of RAM that we can use. and that's going to be able to let us store our programs in there and store data that our programs are going to use. There we go. Connect the read and write lines. No, I don't. I don't have Instagram. Sorry. I do have. I am on what's it called? Hackaday. I did just get approved to be a creator on Hackaday, and I actually if you go on my YouTube channel, I made a video a few weeks about a CPU that I actually like physically built out of transistors. It was pretty cool. It took a long time to do that, but the results were pretty good, I think. But I posted a project page on Hackaday about that CPU, and I did a little. If you go to my posts tab on YouTube, I did a little post in the community tab on that, so you can go ahead and check out my Hackaday page if you want. I don't really have much up there yet, just the CPU project, but yeah, I'll definitely be posting there as I make more projects and as I do more stuff on this channel. And I also have a GitHub where you can find the Logisim schematics and other files relating to my CPU builds and stuff. And I'm and also some of my programming projects I'll put on there as well. So I do have that available. But no, I'm not on Instagram. Unfortunately, people keep telling me I should, but I don't know. Just haven't wanted to deal with it, I guess. Okay, so now that we have that, let's go ahead and string our address lines over here, just above our address decoder. Yeah, and in fact, I can probably also release the circuit files for this CPU that we're building here on GitHub once we're done with it. And I was mentioning this earlier, but I'm pretty sure that the CPU is simple enough that we can just go ahead and build it in one stream. So that's another reason why I chose this particular one to do, because it was simple enough to do it in just maybe a couple hours. So really the most complicated part is what we're doing right now, building the RAM. That's what's going to take the vast majority of our logic gates and stuff, because we're not using any sort of built-in RAM or anything. We're just building everything from scratch, which the I usually don't build RAM units from scratch in Logisim, just because it takes a lot of logic gates to do that, and it kind of bogs the program down a little bit when you do that. But this one's small enough that I think we can get away with it. Just grab the last one over here. There we go. So now we've got our address lines, so we can go ahead and connect them to the decoders. And the idea here is that we can, with both the inverted address lines and the normal address lines, it's possible to connect these to our NAND gates in such a way that for any possible combination of address lines being activated, we're only activating one of the address decoders. So like, for example, this one here, address 0, we can, let me actually do it like this. We can see that, oh, what's going on? There we go. We can see that this this decoder will only get activated if the address is address 0. And then again, if we go over here, the only change really here is that we're activating for address 1. So like if I go over here and I change the address to 1, we can see that this one gets activated instead. And we can just keep going down the line and doing that for each of them. If you know how to count in binary, that makes this process a lot easier because you can just kind of go through and put all of them in the right spots based on, except for I put that one in the wrong spot on accident. There we go. Good thing we caught that now, otherwise that would have given us some trouble later. That's the other challenging thing about building these RAM units out of just logic gates is if you make one mistake in the address decoder, then that'll cause all sorts of problems down the road that are really hard to narrow down. Oh, whoops. This will probably take a while, so you guys probably should get comfy. Hold on, what am I doing? Okay, so where were we? Right. We want to connect this one here, this one here, this one here, this one here. There we go. Now on to the next one. Okay, now we're at address 7. Halfway there. Just got 8 more to go. Address 8. Address 9. Where were we? Address 10? Yeah, I think we're on address 10. Yeah. Now address 11. Address 12. I think we got 4 more to go. Yeah, there we go. We can see the end now. Okay. Address 13. Address 14. And address 15. Okay, so we've got all the addresses 0 through 15 wired up, which means we've got all 16 bytes of our RAM connected, hopefully correctly. We'll go ahead and test it here in a moment. We'll just go ahead and verify that all of our address lines are hooked up correctly real quick by just kind of cycling through all the addresses. There's only 16 of them, so this shouldn't take too long. Okay, address 0 is working. Let's just go ahead and make sure that none of the other ones are, yeah, there we go. Address 1, okay, so that one's working. Address 2 is working. Address 3 is working. Address 4 is working. Address 5 is working. Address 6 is working. Address 7 is working. Go ahead and go on to address 8. Yep, that one's good. Address 9. Yep, that one's good. Address 10. Yep, that one's good. Address 11. Yep, that one's good. Nope. Address 12. Yep, that one's good. Address 13. Yeah, that one's good. Address 14. Yep, that one's good. And address 15. And we're good. Okay, yay, we connected them all correctly, so that's awesome. Okay. Excuse me. So now that that's done, I think what we're going to do, oh, oops, I think what we're, no, go away. There we go. No, stop. There we go. Okay. Okay, so what we're going to do is we're going to go ahead and drag our RAM unit down here to the bottom, and we're going to kind of build the rest of the CPU up above it. That's probably going to be the best way to do what we want here. Before we do that, though, what I'm going to do here, I think, is instead of address input pins here, because this is eventually going to be an address bus, I think I'm just going to go ahead and fix this now by just wiring up some resistors, some pull-up resistors, so that we have the bus ready to go for when we are connecting our address register and program counter to it. No, come on. If I can grab the right spot, there we go. Okay. So that should be good now. Okay. So now we're going to get into building the actual like processor part of our CPU, the part that's actually going to crunch some numbers for us. So let's go ahead and start, I think, by building our ALU. This ALU is going to be really simple. It's just going to be addition and subtraction. So really simple. No need for any bitwise operators here. And then once the ALU is done, we'll go ahead and get to building the accumulator and the instruction register and all that stuff, program counter. So yeah, let's go ahead and start by building an adder. And I mentioned at the top of the stream how we can build any logic gate from different combination of NAND gates, and so we're going to do that same thing here. So we're going to start by building an exclusive OR gate, because that's what we're going to use to build our adders. And somebody way smarter than me came up with this. There's actually if you like Google, if you go on Google and look up exclusive OR gate, there's like a whole Wikipedia article about exclusive OR gates, I think. And on there, you can find this circuit that we're going to build right now. So like I said, somebody way smarter than me came up with this. But it works, so we're going to use it. So if we just connect our NAND gates like so, and then these guys are going to be our inputs. And that's our output over there. So yeah, we can see that if both of the inputs are 0, the output is 0. Either input is 1, the output switches to 1, but if both inputs are 1, then the output switches back to 0. So we have an exclusive OR gate, which is great because we need those to build adders. So we'll go ahead and do that now. We'll just go ahead and copy and paste our exclusive OR gate over here. And this will be our carry input. And then to make the carry output, we can just actually get another NAND gate over here, connect that to this guy here and this guy here, and this will be our carry out. And we can see that all zeros, we have an output of 0. 0 plus 0 plus 1 is 1, and in any combination of that, it's 1. If we have 1 plus 1, we have 0 and carry 1, and again, in any combination of that, it works as well. And if we have all 1s, 1 plus 1 plus 1 is 1, 1, which is 3 in binary, so output 1 and carry 1. So yeah, now that we have that, we can just go ahead and make 7 more of these so that we have an 8-bit adder. Go ahead and have the carry signal go through here. There we go. I forgot to copy the inputs. There we go. Now we're just going to do a simple ripple carry adder here. Nothing fancy. We're not going to bother with any kind of carry look ahead logic or anything like that. Just to keep this circuit as simple as possible. And honestly, if you're like building this thing for real out of like logic gates or transistors or whatever, I don't think having like the highest clock speed, I don't think you're going to be trying to run this thing in the like megahertz range or anything like that, just because it's more of an educational project, really. You're just kind of learning how a CPU works, and probably want to stick to the lower clock speeds anyway, because you want to like watch it run and watch all the operations get carried out and all that. Okay, so we have our adder, and to turn this into a subtractor, we'll just go ahead and add some more XOR gates over here to invert the B operand. Let me just go ahead and get rid of the B inputs first so that we can connect our exclusive OR gates there. We can get rid of all these wires that are kind of just jutting out here. Ooh, there we go. Okay, and then we'll go ahead and just nudge these out a little bit. So that way these can be our subtract input. And whenever this subtract input is on, what's going on here is we're just basically inverting the B input and adding 1. So and in order to add 1, we'll just go ahead and connect that subtract input to our carry input over here. Actually, let's not bother with these inputs at all, really, because the B inputs of our adder slash subtractor, we want those to get connected to the data bus anyway. So we'll just go ahead and pop this over here about there-ish, I think will be good. Okay. So now we can go ahead and connect all of our B inputs to the data bus. And then the A input will just connect to the output of the accumulator once we build that. And the accumulator is just the register that we're going to use to store all of our addition and subtraction results in. Okay, so now we got that all hooked up. Let's go ahead and start building our accumulator now. going to be our first actual CPU register. So we'll go ahead and snag one of these D latches from down here. So that's going to be what we're going to use to kind of form the basis of our registers. And we actually do want this register to be a synchronous register, because otherwise we're going to have to deal with all sorts of problems with race conditions and all that. So we'll go ahead and make a master-slave flip-flop. And we'll have our clock line going up here. We'll connect the clock line here. And we'll also pull down a inverted clock line over here that we can use for the other one. There we go. And then our data input. And then the data input of first stage just feeds into the output of the first stage just feeds into the data input of the next stage. And what that'll do is that'll allow us to edge trigger our input. So we can see that when we change the input around, nothing changes in the output. But when we toggle from low to high on the clock, whatever was on our input gets stored. And then while the clock is held high, we can change the input however we want. Nothing gets changed on the output. And then the next time we trigger the clock, it gets stored. So that's the behavior we want. That'll let us do what we want and avoid race conditions and all that. I'm going to take a look at the chat, see if anybody's said anything else. Okay, yeah, no, nothing that I probably need to respond to. If you guys have any questions, feel free to post them in the chat, and I'll try to answer them. Or feel free to just hang out while we're doing stuff over here in Logisim. Okay, so actually no, I messed up. We don't want to do that yet, because what we actually want to do is we want to be able to where was I? We want to be able to choose whether to store the input or the output of the ALU or the bus or whatever's already in the accumulator. So for that, we're going to need a multiplexer. And multiplexers are actually really easy to build out of NAND gates. We just need one gate for each input line of the multiplexer, and then a NAND gate to just kind of combine all of them together. So we'll just go ahead and do that. There we go. Okay. Now this first one will just feed the output of the accumulator back into itself. This next one we'll just take from the ALU. And the last one will be our input from the data bus. And that'll just let us choose where we're storing data into the accumulator from later. And we'll just go ahead and put some select lines up here. go ahead and call this one STO because that stores data from the data bus. And we'll call this one op because that one we want to activate when we're doing an ALU operation. And we'll actually do some logic here to make it so that when neither of these is on, we'll just automatically have the other one be on and just store the value that's already in the accumulator. And to do that, we're going to have to finagle it a little bit because we're only allowed to use NAND gates. So go ahead and invert both of the inputs of the NAND gate to make an OR gate. Oh, come on. Work with me here. There we go. And then we can output or invert the output to make a NOR gate. And that'll give us what we want, I think. Well, we'll go ahead and verify that here in a second, but I'm pretty sure that'll work. Then we'll just connect both of those up there. Okay, so when either of these is on, that should turn off the other one. Yeah, there we go. That seems to be working just fine. And now we'll scooch everything over a little bit just to make room for connections to the data bus. And if we need to, we can move these back in a second. But yeah, we'll just go ahead and copy and paste this a few times. So we have 8 of them. Oh, that works out really well, actually. That's like just barely enough room for everything to fit there. That's good. I was kind of worried that that wasn't going to fit there for a second. Okay, there we go. Now let's go ahead and hook up all of our select lines. Hook up all of our clock lines. And make sure we connect everything to the data bus. I think I did these backwards earlier, but that's okay. We're far along enough now that I won't worry about it. Just have to remember that we did it that way. Okay, so this one goes to that one, and then we just keep going up the line. And there we go. I think that's everything. So now we'll just kind of scooch this in a little bit. That way we don't have a big gaping hole there. There we go. Okay, so our accumulator is mostly done. There's still a few things that we need to do. We need to connect all of the accumulator outputs to the A inputs of our adder subtractor ALU thing. Excuse me. Let's go ahead and move this out of the way so we can do that. Get rid of all these input pins so we can take our input from the accumulator. And we'll just kind of yoink it up from there. Yeah. And this is actually where we're going to start diverging a little bit from Ben-Eater's design. Ben-Eater, he used two registers actually to do this. He used an A and a B register, and those registers fed input into the ALU, and that worked fine, and maybe made it a little bit easier for people who are new to CPU architecture to see exactly what was going on, which is probably why he did things that way. But it's actually, it makes it so we can build out of simpler hardware if we don't actually do that. If we just use one register and take the other ALU input from the data bus, that makes it so we don't have to store into two separate registers before we do an ALU operation. So it both saves us on hardware and it saves us on clock cycles when we implement our instruction decoder later. So that's kind of why I prefer to do things this way. Okay, so let's go ahead and bring that one down there. Bring that one down there. Let's keep going down the line. Oh wow, it's already 9 o'clock. We've been doing this for like a whole hour so far. Well, you know what they say, time flies when you're having fun. Okay, sorry about that. I just had to check something. Okay, so now we have our accumulator and our ALU all wired up. So now the only thing we have left to do to complete our accumulator is just to let it output to the data bus when we want to, and we'll just use that same open collector stuff that we used down here in the RAM unit to do that. So yeah, we'll go ahead and connect our NAND gate to the inverted output of the accumulator. Just keep copying that down the line. And then we can add a control line here that lets us output to the data bus when we want to. Let's actually do that the same way, same order we did earlier, even though it's backwards from how I usually like to do it. We'll just keep doing it that way, just to keep consistent. All right, and we'll just go ahead and call this our output enable. Well, I guess we're going to have multiple things outputting to the data bus, so we'll go ahead and be specific. We'll have it be accumulator out. There we go. Okay, so with that done, let's go ahead and zoom out so we can take a look at what we've got so far. So we've got our RAM, we've got our ALU, and we've got our accumulator. So really the only things left to do is we need an instruction register so that we can store instruction codes during execution. We need a program counter. We do also need an address register, but I think we'll go ahead and use the instruction register as an address register, and that'll probably make sense more here in a little bit. We also need someplace to store CPU flags, so we can make a CPU flag register. Let's actually make the CPU flag register next. I think that's kind of a logical next step. Go ahead and move. Oh, I forgot to label that one. That's our subtract line. Okay, let's go ahead and move all of our control lines up and out of the way so we've got room for our flag register. Come on. Okay. And this is just going to be another synchronous register. So we'll just go ahead and grab one from down here. One of the nice things about working with computer hardware like this is oftentimes you can just kind of copy and paste different parts of your CPU into other parts, because a lot of it is just copying a bunch of identical things that do different things in different contexts. Okay, and I don't think we need a 3-to-1 multiplexer here, so we'll just go ahead and delete that and have a 2-to-1 multiplexer instead, because we don't need to read anything from the data bus on this one. You just need to read CPU flags. Okay, so that'll be good there. And we'll copy another one. We're gonna have two flags in this CPU. We're gonna have a 0 flag and a carry flag. The carry flag is actually already taken care of. That's down here. So we can just bring that up and feed it into our flags register, and that'll be our carry flag. The 0 flag is going to be a little bit more tricky because we can only use NAND gates. Usually the way you would do a 0 flag is you would NOR together all of the outputs of the ALU, and that would be your 0 flag. But since we don't have NOR gates, we're going to have to do some shenanigans with inverting the inputs of a NAND gate and all that. So we'll go ahead and make an 8-input NAND gate. And I think it's probably going to be easier if we have this face north. Yeah, there we go. He'll be upside down, but it'll be fine. Let's see, how do we want to do this? Yeah, I think we'll just move that out of the way so we're free to move this up a little bit. And then we'll pull in some NOT gates. Have those go north. No, no, didn't want to do that. I wanted to grab it and move it. There we go. You are way too quiet. Oh well, let me see. Let me see if I can go into my stream settings and increase my volume a little bit. There we go. Let me know if that's any better. Thank you for letting me know about that. Yeah, is that any better in the chat? Will you let me know about that? Okay, cool. Thank you. Sorry, this is my first live stream and I can't really hear my own audio. So yeah, if any issues like that come up, please let me know because I want the audio to be good for you guys. Oh, whoops. There we go. Just connect them all up like this. Yeah. NAND gates must be universal. Yes, they are universal. You can use NAND gates to build anything. You can build any logic gates out of NAND gates, which is kind of cool. That's kind of why I well, not why I'm doing this stream, but kind of one of the fun things I'm doing on this stream is building Ben-Eater's CPU out of only NAND gates and making a little few improvements on the way over his design. I think. I mean, I guess whether it's better or not is kind of subjective, but yeah, we're just making a few little tweaks to the architecture that I think make it a little bit simpler to build and simpler to or easier to understand maybe. Okay, so we have our janky little NOR gate built out of an AND gate and a bunch of inverters. Can Logisim compile into a hardware descriptive language? Yes, I think you can compile Logisim into Verilog if I'm not mistaken. I don't know if the version of Logisim that I have can do that. I know there is a version of Logisim that can do that, but I've never really messed around with that. I'm honestly not too familiar with Verilog. Like I know it's a thing, I know it exists, but I've never really done anything with it. But yeah, that is an option that you can look into if you so desire. Okay, where were we? Okay, so we've got all our CPU flags. Those will be useful later when we build our control units. So that way we can do conditional branching. Technically, you only need one CPU flag to do conditional branching and make your machine Turing complete, but Ben-Eater's CPU uses both a zero flag and a carry flag, and that's what we're going to do here too, just because it makes it a little bit easier if we have to. That way, certain things you can do with less instructions if you have access to both of those. In fact, in the CPU that I'm building on my channel, the other one, the Chameleon CPU, we have 4 CPU flags. We have a zero flag, a carry flag, a negative flag, and an overflow flag, and those 4 allow us to do a a lot of what we want to do. But we'll just stick with the 2 here because that's really all we need. And with only, we'll see later that we'll have 4-bit opcodes in our instruction set, so we only have 16 different operations we can build. So really minimizing the number of CPU flags that we're dealing with is going to be beneficial anyways. Okay, so now that that's done, let's go ahead and build our instruction register. That's going to go ahead and store all of the instruction opcodes that we're going to be dealing with during execution. And we can actually go ahead and make this register asynchronous. We don't need a synchronous register here because it's not going to be like feeding back into itself at all. So we're not going to be dealing with any race conditions. So that'll make it so we can have this register be a little simpler than our accumulator. So let's go ahead and grab this over here. We'll have this be our instruction register input enable. And that will just asynchronously load whatever's in the data bus into the instruction register. So let's say instruction register input enable over here. Get rid of all these stray wires going everywhere. And we'll go ahead and connect it up to the data bus. There we go. Nice work, although very long assignment. Yeah, this is going to take all. We're actually almost done though. Once we get our instruction register up, the only thing we really need to do is we need to add our program counter, and we need to do our instruction decoder. The instruction decoder might take a while just because there's going to be lots of different instructions we're going to need to decode. Is it going up to 10 gigahertz? No, unfortunately, Logisim will only let you run it like maybe a few kilohertz. But that should be more than enough to do what we want. Okay, so we have our instruction register. The basic instruction format is going to be, we're going to have a 4-bit instruction opcode that's going to go in these higher 4 bits of the instruction, and then we're going to have whatever operand our instruction is going to work on be in these lower 4 bits, and that's going to be either a excuse me, either a immediate value or a memory address. And so what I'm actually going to do is I'm going to right now, actually no, that's not what we want. We want to bring some open collector gates over here. So that way we can interface with the data bus and the address bus. And I'm going to, oh, come on, stay where I want you, please. I'm going to bring these over here. And these are going to let me put the lower 4 bits of the instruction register out onto the address bus. I'll just go ahead and wire up a control line here to those. And we're going to do kind of the same thing with the data bus. We're going to allow the lower 4 bits of the instruction register to get output onto the data bus, and that's going to let us do some things with immediate values, which will be nice, which will be real handy. Yeah. So go ahead and pull up a control line here. And this is going to be our instruction register address. And doing things this way is just going to let us build things without having to do a completely separate register for the address register, like Ben-Eater did. So it'll let us do things in a little bit simpler way, which is what we want. Okay, so let me just remind myself where the address lines are. Okay, so these lower ones are the address lines, and these upper ones are the inverted address lines. So what we want to do is we want to go ahead and have these address lines go up here. There we go. Okay, so that should be all we need there. And I'm actually going to move these over a little bit so we have room for our data bus connections here in a moment. Okay. So now we're going to... No, we don't want that. We want just the NAND gates, not the connections. There we go. So we're going to have some more NAND gates over here. And we're going to connect these up to the data bus. And we also need some NOT gates. Well, I guess we can just put some NAND gates down here regardless. Just because we're only interfacing using 4 bits, we're gonna do things this way. There we go. Yeah, this is how you would normally make a NOT gate out of an AND gate, just kind of tie both inputs together. We haven't done that in other places on the circuit just because it gets a little messy, but just to kind of demonstrate how that would normally be done. I've been kind of justifying using inverters on other places in the circuit because inverters are basically just one input NAND gates anyways. So it doesn't really make too much of a difference, at least in my mind, but yeah, that's how you would do that if you wanted to like strictly use like only NAND gates. And then we can bring these down to the data bus. Let's actually have another control line up here real quick though, and that'll be our instruction register data because we're outputting to the data bus. Nope. There we go. Okay, so we'll bring this down to the data bus. And we'll just kind of keep going down the line and connect all the data lines. Come on, there we go. Yeah, I mentioned this earlier, but Logisim is great, but it can be finicky sometimes. If you don't like put your mouse in exactly the right spot where it wants you to, then you can get some weird little glitchy things happening. But for the most part, it's pretty good. There we go. And I'll go ahead and move these address lines over a little further so we can differentiate those. Get rid of those little artifacts there. Okay. So now that the instruction register is done, let's go ahead and start working on our program counter, I think. And that we'll just have a 4-bit program counter because we're only working with 16 bytes of RAM. So there's only 16 memory locations to choose from anyways. Yeah. So let's go ahead and bring over, let's actually bring over one of these guys. I think it might be a little easier. Okay, so we want our program counter to be able to increment a value, to increment its value, and we also want it to be able to store values from the data bus, so that way we can, or let me think about that for a second. Do we want to store from the data bus, or do we want to store from the instruction register? Because it might be easier to just store directly from the instruction register. Yeah, let's store directly from the instruction register when we want to jump somewhere. I think that'll be a little easier than interfacing with the bus. So yeah, well, I'll just go ahead and make the decision now that we're going to do that. But first off, let's go ahead and build an incrementer so that way we can count. And to do that, we're just going to go ahead and steal one of these XOR gates that we built over here. And put that. Yeah, I think we want a little more room than that. So yeah, we'll just, actually no, we can scooch up a little closer because we just have this over here that we can pull from. There we go. And then instead of pulling directly from the output, we'll pull from the output of this XOR gate. And then we can have a little inverter going there. That will invert the NAND gate into an AND gate, and that'll give us our increment signal. Yeah, there we go. Yeah, that should work pretty good. And then we'll have our increment going here. We can just copy that over a few times. So that way we got 4 of them. Okay. So let's just go ahead and connect up a separate clock here so that we can do some testing. And we can actually get rid of this guy because we don't need that to go anywhere. Yeah, there we go. And we need an inverted clock line over here. And we have some data inputs here. Sorry, I'm just wiring all these up so I can test it to make sure it's working before we commit to it and wire it up to the rest of the computer. Wire up our control signals. Okay, this will be our input enable for the data lines on the program counter, and we'll go ahead and invert that over there. So that way, whenever we're not reading into the program counter, we're just either keeping it the same or incrementing. Yeah. Let's go ahead and add a reset input over here. And then we're going to need to scooch some things over. That way we can, yeah, that'll work. Okay. Now I can never remember which one I need to connect to in order to get it to reset. So we'll just try both of them on one real quick, and then we'll copy that over. So we'll connect our reset line over there and over there, and we'll see if I got lucky and guessed right this time. And this is actually an inverted reset line, so it'll reset when it goes to 0. And it looks like, yeah, I guessed wrong. We just reset it to 1. We don't want to reset it to 1. We want it to reset to 0. So go ahead and change that around. Swap it to the other ones. Okay, so now we can just do that same thing for all the other ones. Change those to 3 inputs, and then have our reset signal. Oh, come on, what are you doing? There we go. Come on. And have our reset signal go to those. And now, whenever the reset signal goes low, our program counter will reset to 0. And if we toggle the clock like this, nothing happens, which is good. And then if we have our increment input, we toggle the clock, we should see it start counting, and that's all working great. Now let's see if we can load a value into the register. Yep, that's all working as it should. And load a different value. Yep, that's working good. Okay, so I think we can go ahead and just connect this up to where we want now. And we'll go ahead and label this one program counter input enable. And we'll label this as inverted reset and program counter increment. Okay. Let's get rid of this temporary clock here and connect up and over to the main clock, which we're going to have to move up a little bit to get it out of the way. Okay, there we go. Let's move all these other control lines up and out of the way. There we go. Toggle the reset button because I don't like seeing red if I can help it. There we go. Okay, so now we can get rid of these data inputs and just take our input directly from the instruction register, because the instruction register is going to hold our jump targets for us. Move these down just a little bit. Oh, that's annoying. Okay. Looks like it's not going to let us move just a little bit down without weird artifacts. So we'll just go ahead. Oh, what happened there? That's weird. Yeah, every so often Logisim will wig out and think that it needs to just randomly connect something somewhere. Isaac Clark. Oh, hey, is that the Isaac Clark? How you doing? I know an Isaac Clark. I'm wondering if that's the same one I know. Oh, and it looks like it got all funky over here. Let me just hit undo a few times because that's unfortunate. Nice. Okay. Well, thanks for joining, Isaac. Good to see you. Unrelated to this stream, have we heard about Pathfinder tonight? Are we still doing that? Because I should be available. Cool. What is going on? That shouldn't have happened. Let me just fix this real quick. But yeah, Isaac, just for your information, a Ben-Eater is another. He's another YouTuber that does like computer hardware stuff. So a Ben-Eater CPU is a CPU that's kind of based on his designs. What is going on? Yeah, Logisim is freaking out on me right now for some reason. I'm gonna have to figure out how to fix this. Yeah, and right now what we're doing is we're building a CPU that kind of follows his design philosophy, but we're making it only with NAND gates, and I'm also making some improvements to the architecture to make it a little bit simpler. There we go. Okay, now where were we before it started reading out? That's right. We were connecting the program counter over to the address, or not to the address, to the instruction register. I'm gonna have to get a little squirrely with some of the connections here. There we go. And now we can go ahead and scooch this in. There we go. Okay, so our program counter's almost done. We still need to wire it up so it can connect to the address bus, though. So we're just going to go ahead and yeah, there we go. That should do what we want. Move some NAND gates over here. Where is it? There we go. And we'll have this be program counter address because we want to output the value of the program counter to the address bus when that input is on, or when that control line is on, excuse me. And yeah, that should do what we want. So we can just go ahead and connect all of the address lines up like so. There we go. Okay. So just go ahead and get out of here. Don't want to see all that political stuff right now. No, too far. There we go. Okay, so let's take a look at where we're at now. So we have our RAM, we have our arithmetic logic unit, we have our accumulator, we have our instruction register, we have our program counter now, and we have our flags. So I think we have all of the registers we're going to need. So really the only thing left to do is to build our instruction decoder, and that'll let us activate the right control lines in the right sequence to execute all the instructions we want. But before we go ahead and do that, let's go ahead and come up with a list of instructions that we want to be able to execute, just to kind of, so we have a roadmap to moving forward. This is probably going to be the most complicated part of the build, just because this is going to be the brains of the operation a little bit. So I'm going to go ahead and open up a little notepad here. Yeah, so let's go ahead and list out all our opcodes. We have 4-bit opcodes, 0 through 15. Okay, so we have all 16 opcodes there. Okay. We'll go ahead and have opcode 0000. We'll go ahead and have that be a no op. And that'll just do nothing. 0001. We'll have that go ahead and be add, and that instruction will just take whatever's in the accumulator and add it to some memory location, or add to it some memory location. We'll go ahead and have the next one be a subtract instruction. Now, that's the same as the add instruction, but we'll just go ahead and subtract instead of add. Then we'll do an add immediate instruction, which is the same as the add instruction, but with an immediate value instead of a value from memory. Same thing with subtract immediate. So those will be all of our arithmetic operations. Now let's go ahead and add some memory operations. So we'll go ahead and have a load instruction, and that will just take a value from memory and load it into the accumulator. We'll also go ahead and have a load immediate instruction, and that'll just take an immediate value and load it into the accumulator. We'll have a store instruction that'll take the value in the accumulator and store it to some memory location. And then we're going to have jump instruction, and that'll just jump our program to a different place in memory. Let us do like loops and stuff, which will be nice. We'll go ahead and have a branch if carry, which will be the same as the jump instruction, but it'll only jump if the carry flag is on. And just because we'll go ahead and have a branch if not carry, and same thing with the 0 flag, branch if 0 and branch if not 0. And now we got 3 more opcodes left that we could fill. Trying to think if there's anything else we want our CPU to be able to do. I think let's just go ahead and leave those ones empty for now. We can fill those later if we want. We will go ahead and have a halt command though. That'll let us stop executing when we hit a certain point in the program. Okay. Now that we have that, we can start building our instruction decoder. And to do that, we'll go ahead and take some NAND gates over here. We'll have 16 of them for 16 possible opcodes. Although we do have 2 that are blank right now that we can go ahead and decide what we want those to do later if we want. We'll have these take 5 inputs for our 4-bit opcode and an additional enable signal. So we'll go ahead and have 16 of those right here. Oh, that's a bit too low. Okay, so we'll go ahead and stick that up here. So we don't want that to collide with our data bus. Yeah. Now we'll just bring those right over here. And then as input to our instruction decoder, we'll just take that directly from the instruction register, because that's already storing our instruction opcode anyway in these highest 4 bits here. And we actually already have the inverted instruction opcode here in our instruction register as well, so we don't even have to worry about any inverters to make our inverted opcode. So we'll just go ahead and snag these over here. And then same thing with the inverted opcode. We might have to get a little creative with wiring now. The space is going to get tight pretty quick, I think. There we go. That should give us enough room. Bring these over here. Oh, whoops, something's not right. Oh, I missed one. That's what's going on. Okay. There we go. All right, so we've got our opcode over here. So now we can just go ahead and what just happened? There we go. Now we can just go ahead and make some adjustments over here. Sorry guys, this might take a moment, so just bear with me. Okay. Okay, so we have our opcode right here. And now let's just go ahead and extend these over here. This is going to be our inverted opcode. Come on, there we go. Okay, so now we can start, well, let's actually label these before we get going, because that's going to make it a little easier. Just, oh, come on, drag this over here. And then drag all of these opcodes that we defined over here. There we go. So this one will be our no op. If I can get it to work here, there we go, no op. This one will be add subtract, add immediate, subtract immediate, load immediate. Oh, did it go? No, it didn't. Okay. Load immediate. There we go, that went. And then our store instruction. And then we have our jump. Branch if carry. Branch if no carry. Branch if 0. Branch if not 0. And then these two ones that we haven't figured out yet. We may not even use those, we'll see. And we have our halt. And now we just need to wire all these up to the right places. Just remember, okay, so yeah. We have our opcode over here on the right and our inverted opcode over here on the left. And this will be just a moment, guys. Again, bear with me. Got to wire up all 16 of these guys. So it's going to be a moment. Logisim is unfortunately starting to lag on me just a little bit, but luckily we're almost done, so we don't have too much more to add. Okay, we're up to 7, so we're halfway there. Eight. I'm gonna have to get a little creative with rerouting some of these wires, I think. Yeah, let me just go ahead and reroute some of these real quick. Get them out of the way. There we go. Oh, what just happened? Oh, I connected one of them to the wrong place. There we go. That was my bad. Come on. Did I do that right? No, I did not do that right. Okay. There we go. That's better. Okay, just 3 more to go. There we go. Oh, I done did it again. Move those over. This doesn't really matter if those are all like connected to the exact same ones, but just it'll bother me if they're not. Okay, get rid of all these dangling ones we don't need. And then we can connect our enable line over here. This will come in handy later. Okay, there we go. Okay, so now we've got all of our opcodes wired up. So we can start working on the instruction sequence now. And I mentioned at the top of the stream that I was going to try to make the instructions in this machine execute a little bit more quickly than Ben-Eater did with his machine, because a lot of his instructions took like 5, 6, 7 clock cycles to execute. I think I'm going to try and get my machine down to executing all instructions in 2 clock cycles. So the instruction cycle for each instruction is essentially going to look like just during the first clock cycle, we're going to fetch the instruction from memory, and load it into the instruction register, and then during the second clock cycle, that's when all of the execution of that instruction is going to happen. And I think we should be able to do that all in just the 2 clock cycles. But in order to get that to happen, we're going to need another flip-flop over here. So we'll just go ahead and snag one of these guys from our program counter and bring it up over this way. Yeah, there we go. And then we'll connect our reset up over here. Where's that reset line at? There it is. Okay. So we'll connect that to our reset. And for the data input, we'll just connect that to the inverted output, so that way every time the clock cycles, it'll just toggle between 1 and 0. And then we have our clock line up here. Okay, let's go ahead and reset that. Oh, what's going on? Why aren't you working? Oh, because it, for some reason, decided it wanted to connect itself down here. Okay, I see. There we go. Okay. Cool, so now that that's all connected, let's see if we can get both of these into the same spot on the screen. Okay, so yeah, if you look down here at our flip-flop, we can see that every time we toggle the clock, that just changes state from 1 to 0. Reset it. Okay, so basically what that's going to allow us to do is whenever this flip-flop here is in the 0 state, that's going to be our fetch cycle. So that's going to be when we're going to load the instruction into the instruction register. And then when this flip-flop is a 1, then during that clock cycle is when we're going to execute that instruction. So I think in order to do what we want to do next, we're going to have to organize all of our control lines into our control bus. That'll just make it easier to build the rest of our instruction decoder. Let me just do that real quick. So we've got our subtract control line. We got these 2 control lines. Just fix that real quick. There we go. The clock is fine where it's at, I think. That's not technically a control line. We got the accumulator output control line. You got the instruction register input enable. Instruction register output control lines. Program counter input enable. Come on, there we go. bump that up just a little bit. Program counter increment. And program counter output. Oh, that's weird. Okay, there we go. So we have our control bus. Now each one of these control lines is going to get its own NAND gate in our instruction decoder. And that's going to control when each of these control lines gets activated in the instruction sequence. So I'll just go ahead and list these out over here. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 control lines. So we need 10 NAND gates. Just put labels on all these so I can tell what they are. I wonder if I can... No, it doesn't let me change where the label is. That's unfortunate, but we're just going to have to deal with it, I guess. Oh. There we go. It was just wigging out on me for a second. Copying all these labels over from the control bus. And then once we've wired up all these NAND gates in our instruction decoder, then we can get rid of these control pins because these lines are all going to be automated by the instruction decoder anyways. So we won't really need to worry about controlling them manually. Okay. Let's go ahead and drop these over here. Oscillation apparent. Okay, well, let's go ahead and reset things so that it's no longer happening. Okay. So let's go ahead and space these out a little bit because some of these are going to need quite a few inputs. Oh, and it actually occurs to me that we forgot one control. We forgot a couple control lines over here. Even we forgot the read and write lines, but we can just go ahead and pull those directly over here when we're ready. Okay. So now let's go ahead and make some more for our read and write lines. So that'll control when we read and write to and from RAM. And let's go ahead and move these up like so. There we go. Okay, so now we can go ahead and connect up all of our control lines. Make sure I connect the read and writes up to the right ones. Yeah, read is on top and write is on bottom. There we go. That's easy enough. And now we can get rid of these. And now the rest of the control lines can just get hooked directly up here. And we'll go ahead and connect these last few ones up. And then once we're done with that, all of these gates, they'll just let us decide basically which control lines we're activating for which instruction. So that's really the last thing we have to do, and then our CPU will technically be complete. There's still a little bit more we have to add in order to be able to program it though, but that shouldn't take too long. And then after that, we'll just write some test programs, test things out, wire up some output. And that'll basically be everything we need to do, I think. Let's get rid of these dangling ones over here. And I might come back in a moment and shrink these bus lines down. In fact, let's do that now while I'm thinking about it, just because I think it'll look a little cleaner that way. Oh, come on. That's annoying. Yeah, sometimes when you're zoomed out like this, if you don't have your mouse like on exactly the right spot, then it won't work. I haven't checked chat in a while. Let's see what's going on there. Okay, nothing new. Come on. No, that's not what I wanted. There we go. Okay. So now that that's done, okay, we can start wiring up our instruction decoder to execute our instruction sequence. Like I said earlier, the first thing in each instruction cycle we want to do is we want to take the instruction from RAM and load it into the instruction register. And we're always going to do that no matter which instruction we're executing, so we don't even really need to worry about these decoders here. We can just always do that whenever we're on the first step of the instruction sequence. So let's go ahead and take this inverted line here, bring it down here, and we're going to go ahead and connect this. No, we want to we want to do this one, right? Because we're working with NAND gates, not OR gates. Usually when I'm building instruction decoders, I do it with OR gates, and that makes it a little easier to think about. But since we're only using NAND gates here, I have to kind of switch things around in my brain a little bit. Okay, so during the first step of the instruction sequence, we want to load from RAM into the instruction register. So we want to put the value of the program counter out onto the address bus, because that's the memory location we're reading from. We want to increment the program counter, so that way we're pointing to the next instruction after we're done. We don't want to input into the program counter. And we do want to input into the instruction register. And we also want to read from RAM. Okay. And I think that should be everything we need to do during the first instruction cycle. And then everything else will just depend on which instruction we're doing. So we'll just go ahead and connect that to our decoder enable line, and that will enable our decoder. So for the no op instruction, we literally just do nothing. So that won't really get connected anywhere. In fact, we can probably just delete this whole NAND gate here. But we'll do that later. We'll just keep there just so we know we have it. For the add operation, what this one is going to do is we want to take the address that we're pointing to in the instruction register and add the value at that address to the value in the accumulator. So what we want to do for this one is we want to have the address register output, or not the address register, the instruction register output an address to the address bus. We want to do an ALU operation, and while we're doing that, we want to be reading from RAM. And the subtract instruction is exactly the same. The only difference is we want to have the subtract signal enabled as well while we're doing the subtract operation. Go ahead and add a bunch more inputs to that one because we're going to be using that one a lot. Okay. And then for the add immediate instruction, that's going to be the same as the add instruction, except we're not getting the value we're adding from RAM, we're getting it from the instruction register. So what we want to do in that case is we want to have the address register output to the data bus. Not the address register, the instruction register, sorry. And then everything else, yeah, we don't want the address register output, or the instruction register output to the address bus. We want it to out to the data bus, and we want to do an ALU operation. We don't need to read from RAM. Just add a few more inputs to this one because we're going to be using this one a couple more times. And we'll just go through this process for all 16 operations we want to do. Once we get down to the conditional branch instructions, there'll be a few extra things we need to add, but it should be pretty simple for the most part. And then the subtract immediate is going to be the same as the add immediate, except for we're also going to enable the subtract signal. In addition to everything else. For the load instruction, we want to load a value from RAM into the accumulator. So what we're going to do there is we're going to have the instruction register. Oh, we got some new chats on there. What is a Ben-Eater CPU? So I explained this a little bit earlier on the stream, but Ben-Eater is another YouTuber that does like computer hardware and programming stuff. And so he on his channel built an entire CPU out of some logic gate chips, like the 7400 series logic chips, and he built that on breadboards. Did a whole series about that. And so a Ben-Eater CPU is just a CPU that uses kind of the same design philosophies that he did, because his was really good at like teaching people the basics of CPU architecture and all that. This one that I'm building here is just essentially the same CPU that Ben-Eater built, except for it's built only out of NAND gates, and we're making some minor tweaks to the architecture to make it a little simpler to make. Yeah, so hopefully that answers your question. And right now we're almost done building the CPU. We're just wiring up the instruction decoder, so that way we can start executing instructions. Okay, so we're on the load instruction. So during the load instruction, we want the instruction register to output to the address bus. We want to read from RAM, and we want to store a value into the accumulator. And for the load immediate instruction, it's the same as load instruction, except for we're getting the loaded value from the instruction register and not from the data bus and from RAM. But yeah, any of you that have never seen or that are interested in like computer hardware and low level programming and all that, if you've never seen Ben-Eater's videos, I'd highly recommend checking them out. He's really good at what he does. I'm not like associated with him at all. He doesn't know that I'm like promoting his content at all, but like his videos are great. You should check them out. Okay, so we're out and we're having the instruction register output to the data bus, and we're storing the value from the data bus into the accumulator. And then for the store instruction, we want to store the value of the accumulator somewhere in RAM. And that's going to be pretty much the same as the load instruction, except for instead of storing the data bus into the accumulator, we're storing the accumulator into RAM. So for that one, we want to output an address to the data bus. We want to write into RAM. And we want to have the accumulator output its value onto the data bus. And then for the jump instruction, we'll actually lump this together with the branch instruction. So what we're going to do for these ones is we're going to take our carry over here. We're going to bring it down over here. And we're going to do the same thing with the inverted carry. And for the 0 flag, and the inverted 0 flag. So we have our 4 branch conditions over here now. We have the carry, no carry, and 0 and not 0. And we want let me think about how I want to do this here. I'm thinking maybe the best way to do this, because otherwise we would have to do a whole bunch of finagling with inverting the inputs of a bunch of NAND gates, and I don't think we really need to worry about that. I'm pretty sure we're not going to use these ones anytime soon, so I'll just get rid of them for now so we can make room to expand these ones just a little bit. So what we're going to do is we're going to add a couple of inputs to these branch instruction decoders. So that way we can selectively enable them depending. Oh, what just happened? Depending on whether we need to branch according to that specific instruction. That might have just screwed a bunch of stuff up, actually. Hold on. Let me undo a couple of times. Okay. What's going on here? Let's maybe try and do these one at a time so Logician doesn't freak out on me. Bring these down here. Space them out a little bit so we have room to put some more lines up to them. Why didn't it grab those? I think we might be able to just leave this one where it's at. Yeah, I think we'll be fine there. We'll just need to move some of these over. Yeah, there we go. That'll work. Except for that, I don't know. That's kind of bothering me with it being so close to that other one. So I'm going to see if I can't just scooch it over a little bit. There we go. That's better. And then we can move those all back over to where they were. Sort of. Okay. Now we can add some inputs to these ones. Let me just fix the wiring real quick. Why didn't it grab them? There we go. Yeah, sometimes when you've got this much going on in one circuit in Logisim, it can get a little buggy sometimes. There we go. Okay. So now we can come down here, and this is our carry signal. So this gate will only be active when we have a carry signal. And then same thing down here for all the other ones. No carry, 0, and not 0. There we go. Yeah, that should do what we want. And then we are gonna have to do some finagling with NAND gate inputs here because we want these. We're just going to combine all of these jumps and branches into a single jump control line. As far as our instruction decoder is concerned, it'll just have like one control line that says, "Hey, we need to jump," and then that's going to be based on whether we have a jump instruction or whether we have a conditional branch instruction that needs to branch. And the way we're going to do that is we're just going to I think we can just NAND all these together, actually. That'd be really nice if we can do that. Let me just think about that real quick. No, I don't think that's going to work, actually. So if we were building a normal decoder, these would all be AND gates, and these would all be OR gates down here. And if this was a normal decoder, we would be ORing these together to make our jump input. These are inverted, so we're inverting all of the inputs of an OR gate. So that gives us our NAND gate. But this also needs to get inverted so that it'll be compatible. Yeah, I think we can do this with just an AND gate and an inverter. That should be fine. And if it turns out that that doesn't work, we can revisit it in a moment when everything breaks. But for now, we'll just use this and call it good, and we'll fix it later if we need to. Okay, so yeah, that should give us our jump signal. And when we need to jump, really the only thing we need to do is just load from the instruction register into the program counter, which we already have set up to do over here. The only thing we need to do is activate the right control signal to do that. And that's going to be our program counter input enable. And our halt line, we'll worry about the halt signal later. That's going to be a kind of a special case. That's basically just going to stop the clock. So we'll put a latch next to the clock signal, and when the halt line goes high, we'll go ahead and make sure the clock can't execute anymore until we reset it. But we'll worry about that in a moment. For now, what I'm going to do is I'm going to add a separate control signal over here. I'm going to bring our clock down to our data bus. So this will be our clock. Oh, come on, work please. There we go. And I'll put a control line for programming over here. And let me just go ahead and bring the reset line down here as well. No, it didn't like that. Let's go ahead and raise it above the clock line, maybe that'll help. Okay. So this is going to be kind of our little programming interface over here. Let's go ahead and make sure reset. And when this program signal is on, then we're going to be able to manually write values into RAM. And that's how we're going to program the machine. I'll just kind of lump that in with the control bus, but instead of feeding from a NAND gate, it'll feed into some of our NAND gates to kind of make sure that we activate the right signals so we can program stuff in. Let's actually go ahead and build a NOR gate, or build an OR gate, I mean, with some, what am I doing? Right. And that's going to go in, and that's just going to OR our program signal together with this to go down into our instruction decoder. So that way we're not decoding instructions while we're programming, because that could lead to some contention with other values in the on the control bus. Except for we need that to be an OR gate, so we need to invert the inputs. There we go. Okay, and that should be good there. Just hit reset again. Okay. So now when the program signal is on, we want to be incrementing the program counter. We want to have the program counter output to the address bus. And we want to write into RAM. Okay. Now these oscillations down here that we're seeing is probably because of an issue that I really probably should have fixed earlier on. But we're reading and writing to and from RAM anytime these read and write signals are active. And that can lead to a couple of problems because when like the moment that these read and write signals turn on, there could still be some settling in as far as like the values on the data bus and the address bus. They could still be fluctuating because they haven't stabilized yet. So what we're actually going to do is we're going to take the inverted clock signal over here. See if I can find it. Yeah, the inverted clock signal from over here. And we're going to feed that down into here so that we're only reading and writing to and from RAM when the clock signal is low. And that should hopefully give our data and address signals time to stabilize so we're not just reading and writing a bunch of garbage to a bunch of garbage locations in RAM all the time. So that's just going to take a minute to do that. Oh, no, don't move. I just want to select you. Thank you. There we go. Okay. And now we need to go to each of these and connect up the inverted clock line up to these NAND gates, if it'll let me. Sorry, this is going to take just a moment. And then once this is done, we're actually probably just about ready to start writing some programs for this thing. We just need to connect some kind of output to it. I'm thinking probably just doing some simple memory mapped output, just letting us directly see what's in the last location in RAM and using that for our kind of output register sort of thing. Yeah, there we go. Okay. So yeah, let's actually do that right now. So what we're going to do
So we're going to go over here into the wiring menu. We're going to grab a splitter. What I could do is I could actually just make a whole binary to decimal decoder, but that would take a long time and a lot of logic gates. We don't have time for that today. So what I'm going to do is just simply combine all of these into one line and then bring it over to our programming interface so we can just directly see what's in the last byte of RAM. Okay, and then we're going to make this an 8-to-1 splitter. So we want 8 fan out and 8-bit width. Now we're going to go ahead and turn it around. No, that's the wrong way. No, that's the way we started. Okay. There we go. And we're going to make it right-handed. So the output of the splitter points down. There we go. That should give us what we want. More or less. Just trying to figure out where I want this to get put. Yeah, that seems like as good a spot as any. And then we'll just wire up all of the data that we want to it. No, didn't want to do that. Yeah, sorry guys, Logisim is lagging a lot right now, so it's taking a minute to think about things whenever I put a wire down. Okay, there we go. So that should give us our output. We'll just kind of string this guy over here all the way over to our programming interface. And we will just pull a probe over here so that way we can see what the value is. And we want it to be unsigned decimal. It's giving us an error value because it's not really giving us any valid data yet. Okay, so I think we should be ready to start writing some test programs here. Yeah, let's just go ahead and write a very simple test program that will just kind of increment the output by 1 and loop around. So what we want to do is we'll have loop. Actually, first, let's load an immediate value of 0 into the accumulator, and then we'll store that value at address 15, which is our memory mapped output. And then we will have a loop. And in that loop, we will load from address 15, and then we will add an immediate value of 1 to increment the value in address 15. and then we will store back an address 15, and then we will jump to the loop. And the loop is going to be at address 012. So we can just go ahead and put that in. There we go. So that'll be our very simple assembly program. Let's start plugging it in and see if it works. So we'll go ahead and reset the machine, put the programming input on. Okay, and now I immediately see a problem. What's going on? Our write signal is having invalid data. Where is that coming from? Oh, I see. We messed up over here. Okay. So what we want is for this to stay off if this is on. Okay, I think I know what we can do here. So we'll go ahead and make a NOR gate using an AND gate and 3 inverters. And then we actually don't need this one because we're going to be inverting that input anyway. Oh, whoops. Didn't mean to do that. Then we'll go ahead and plop this in. There we go. Now everything should be working. And oh, we need to invert these, I think. No? Oh, I see what it is. Okay. Forgot we were using NAND gates instead of AND gates again. Okay, so we need to do that. And we need to have that be an inverted program signal, I think. No, I didn't want to get rid of it. Okay, so the program signal will be an active low signal. Okay, so let's see if that's given us what we want. Okay, I'm seeing another error. So we only want to execute the first cycle of the instruction sequence if we're not programming. There we go. We need that to be inverted. There we go. That should give us what we want. Cool. It's working, I think. Okay, so let's go back to our little program we wrote. Now let's go ahead and just kind of manually assemble this. Okay, so we have 1, 2, 3, 4, 5, 6 instructions to addresses 0 through 5. Okay, so the first instruction is going to be load immediate 0, and the opcode for load immediate is 0110, and then the immediate value 0. Next instruction is store 15. The store instruction is opcode 0111, and we're storing to address 15, and that's 1111. Next instruction is load 15, and the load instruction is opcode 0101. And then the address 15. Next we have add immediate 1, and add immediate is 0011, and the immediate value 1. And then we have store 15. Opcode for store is 0111, and then the address after that. And then we have a jump 2. And the jump is opcode 00, and then the address 2. Okay, so those are the instructions we're going to program into our RAM. Let me go ahead and, yep, we're at address 0. Okay, clock it in. And then address 1, we want all ones except for first bit. I'm sorry, I'm just verifying that that instruction loaded correctly last time, and it looks like it did. Okay, so it looks like we're good. And then at address 2, just need to turn off that other bit there. And then at address 3, we have 0011, 0001. Okay, go ahead and clock it in. And now we're on address 4. And that's again all ones except for the first bit. And finally, address 5 is 0100, 0010. Okay. So now we'll go ahead and turn our program pin off. Oh, what just happened? Well, that's interesting. Now we're getting an invalid signal somewhere. Invalid write signal. What is up with that? Oh, I think I know what it is. We didn't. That's interesting. So it looks like it doesn't like it if we don't. Yeah, because we are on No? Oh. Yeah, that needs to be... Well, hold on. Let me turn the program signal back off and see what's going on there. You know what? I think we connected to the wrong thing here. Let's move to the inverted instead of non-inverted and see what that helps. Turn the program signal back off. Zoom out a little bit so I can see more at once. Okay, so now we're in program mode. Yeah, something here is not working the way it needs to. Okay, so that's all been reset. Yeah, this is where the fun part of the process comes in, trying to figure out what's not working. Have a think real quick. If any of you guys have any ideas, let me know. So we want this signal to be active if we're not programming. And if we're on instruction step 1 and not 0. Yeah, so that works. So this one's fine. It's this one that's giving us problems. So we want this to be active. We want this one to be off if we're not programming, and if we're on instruction step 0. Okay, I think I see what's going on. Okay, I figured it out. We need a separate set of gates over here for that signal. I was thinking we could run it all off the same thing, but nope, we cannot. Okay, so let me just separate those real quick. And we want this one to go over here. And we want to invert that other input for this one. Okay, so that should fix that. Let me just verify real quick that that actually did fix it. Okay, so we're not programming. And we're on instruction step 0, and that's off, so that should be fine. And okay, got there. I'm gonna get rid of this inverter. I bet you that's what's going on. Okay, so let's try all that again. Reset. Okay. Oh, no, that's... Okay, let me rethink our logic here real quick. We want this line to be off if we are not in programming mode and we're on instruction step, well, first instruction step. Okay. So let's go ahead and turn the programming mode off, and we will reset, make sure we're on instruction step 0. Okay, so that's all fine and dandy now. Okay. So let's cycle the clock to put us into instruction step 1. Let's see. Okay, so yeah, that appears to be working now. Cycle the clock again. Yep. Okay, so it's working when we're not in programming mode. Let's see about programming mode. Okay. Yeah, I think we're working now. That's good. Okay, so let's try writing our program into RAM again. Hopefully it'll work this time. Go ahead and reset to address 0. Yeah, thing looks good. Okay, let's go ahead and pull up our program again. Okay, so first we have instruction 0, 1, 1, 0, and then all zeros after that. Cycle the clock. And then all ones except the first bit. Oh, you know what? I think I've been thinking about the data bus backwards too. Hold on. Just have to think. Yeah, these are the low bits. Okay, so we have our... We've been doing this upside down. Okay. Let's reset again. Okay, so yeah, this is the high bit, this is the low bit. So go ahead and clock that in. And then we have all ones except the first bit. And then we just turn that off. And then we have 0, 0, 0, 1, 1, 0, 0, 0, 1. And then we have all ones except for the first bit again. And then our last one. Okay, so we should have our program in RAM now. And let's see what happens when we take it out of programming mode. Hopefully it doesn't blow up on us like it did last time. Nope, it did. Okay, what's going on? Okay, so we have an invalid write signal. Oh. Okay. That's interesting. So something's wrong here now. Let's just rethink our logic here. So we want this signal to be on if we're not in programming mode. And we're on the second instruction set. Okay, so this signal is wired backwards. And now, of course, we have to rewire this one up to the correct one. There we go. Okay. Yeah, that should theoretically fix it. Okay, let's try that again. Reset, put it into program. Third time's the charm, right? Okay. Clock in the first instruction. Clock in the second instruction. Clock in the third instruction. Clock in the fourth instruction. Clock in the fifth instruction. And last but not least, we'll clock in the sixth and final instruction. Clock. There we go. Now, let's take it out of programming mode. Yay, it didn't blow up. Okay. Good, I was worried for a second. Okay, so let's zoom out so we can see what's going on. And reset. So we should be... Oh, I see what it is. We didn't reset the data bus to floating. That's why we're having garbage on the bus. That's okay, because we can just fix that like so. Okay, so we're having our instruction, or well, let's go over to our instruction decoder to see what's going on. Okay, so we're on instruction step 0, which is the fetch sequence. So we're reading from RAM using the program counter, and we're storing the result into, or we're storing that value RAM into the instruction register, which is all working as it should. And then when we cycle the clock, we're moving. Why isn't it working? Oscillation apparent. Where? That's weird. Okay, well, let's reset this and see what's going on. Reset simulation. It's not responding. That's interesting. Might have to save this. Exit out and restart the program. Sometimes when that happens, you just got to do that. There we go. Okay, let's see if we can figure out what's going on. Okay. Well, let's just try an even simpler program. We'll save this program for later. We'll just jump to 0. And that should just be 0, 1, 0, 1, 0, 0, 0, 0. And that's all we should need. So let's see why our instruction sequence isn't working, or if we can figure out why our instruction sequence isn't working. Okay, so that okay, so yeah, the instructions in RAM. Take it out of programming mode. We set our data bus. Okay. So we should be on the first cycle of the instruction sequence. And we're outputting to the data bus from RAM, and we're loading into the instruction register. Okay, that's all working fine. Let's see what happens when we turn the clock on. Oscillations. Interesting. Why are we getting oscillations? That's interesting. Well, they appear to be originating from the instruction register. Maybe we need to do the same thing for our instruction register that we did Yeah, I bet you that's probably what it is. Yeah, we'll do the same clock trick for our instruction register that we did for our RAM. Okay, and the inverted clock is just right over there. And we need to invert that guy as well. Okay. Reset the circuit. And we're in programming mode. So we'll put the jump instruction into there, clock it in. And now we're getting invalid data all of a sudden. Okay, we'll put it in programming mode. Clock it in. Maybe we need to reset it before we do that. I bet you that's probably what it is. And we also need to reset our data bus. Okay, so we're out of programming mode. We've got an instruction in RAM that we're putting into yep. Okay. So yeah, the instruction register appears to be working still. So, and then when we cycle the clock, we don't get any more oscillations. And it thinks we're doing the load instruction for some reason. That's weird. What's our load opcode? Oh, it thinks we're doing the load instruction because I told it to do the load instruction. I put the wrong opcode into RAM. Okay, well that's fine. But where is it loading from? It's loading from 0. Yeah, that seems to be working, even though I told it to do the wrong thing. Okay, let's try that again. Put it into program mode. Put the right opcode into RAM this time. Yeah, I see the issue. I copied down the wrong opcode. Okay, yeah. Okay, problem solved, hopefully. Lock it in. Reset. And take it out of programming. Yeah. So, hopefully, what should happen is we should just keep putting 0 into the program counter. See if that actually happens. Yep. Yep, it's working. Okay. Yay, we officially have a program running. It doesn't do anything. It just is an infinite loop that does nothing. But it's a program and it works. So now let's try doing that other program that we wrote earlier. See if we can get that working. Okay, so we'll put it into program mode, reset it. Okay. Clock in the first instruction, and then we'll clock in the second instruction. Clocking in the third instruction, clocking in the fourth instruction, fourth instruction, now the fifth instruction, and the last instruction. And then we'll hit reset, and we're going to have to reprogram in the first instruction real quick. I think we'll just do that just in case it got corrupted. Okay, and then we'll take it out of programming mode. And we'll see if it works. Oh, somehow we got a value into the other RAM place, even though we didn't want one, but hopefully that's fine. Come on, zoom out, please. Okay. So, first instruction. I forgot to reset the data bus. Okay, so that should be loading 0 into the accumulator. And it looks like it did. And now zero, 1, 1, 1 should be storing. But it thinks we're loading for some reason. Okay, that's interesting. What's going on over here? Well, somehow our program got corrupted, it looks like. You know what? Maybe what we need to do is make an OR gate over here. And make sure that we're always resetting this latch here when we're programming. So that way we don't have to manually reset it, because that's annoying anyways. So that's our inverted reset signal. And we have our inverted program signal already over here. Okay, so now that latch should always be resetting when we're programming, so we don't have to manually reset it. There we go. So let's try putting that program in again. Okay, so the first instruction, plug that in. Second instruction, plug that in. Third instruction, plug that in. And the fourth instruction, plug that in. Fifth instruction, plug that in. And the sixth and final instruction, plug that in. And take it out of programming mode. And set our data bus to floating. Okay, let's just verify that all these instructions are correct. We got 0, 1, 1, 0, 0, 0, 0, 0. That's correct. 0, 1, 1, 1. Yep, that one's good. That one's good. That one's good. That one's good. And that one's good. Okay. So let's try yet again to run our program. Okay, so we should be in the first stage of the instruction sequence. So that's going to load our instruction into the instruction register. Clock. What happened? That's interesting. Okay. So we have 0, 1, 1, 0, 0, 0, 0, 0 in the instruction register. Huh. Yeah, not sure what happened that last time. But we are... Let's reset real quick. So... Yep, that all looks good. Okay. Let's try and figure this out. 0, 1, 1, 0 in the address register. And when we cycle the clock, interesting. Reset again. Oh, that's weird. For some reason our clock line. No, never mind. That's fine. So why? Ah. That's interesting. Something's going on with our reset signal over there. Oh, I know what it is. I forgot that this was an inverted reset signal. So we need to re-invert it back to be able to use it. There we go. Okay, so that should hopefully fix most of our issues. Okay, so we'll reset. And we've got the right instruction in RAM, or not in RAM, in the instruction register. And when we cycle the clock, we're doing load immediate 0. Which we did. And now we're loading the next instruction into the instruction register, which it looks like is correct. And we have 0 in the output, which is good. That's what we want. Now the next instruction should be to load address 15 into the accumulator, which should just load 0 back into the accumulator. Well, somehow 0 got loaded into the instruction register. That's interesting. Which instruction are we on? We're on instruction number 3. Yeah, did that one get corrupted somehow while we were fiddling with stuff? 3. Yeah, it looks like that one got corrupted. So we're going to need to reload our program back into RAM. Should take just a moment. Reset program. Okay, first instruction. Second instruction. Third instruction. Fourth instruction. Fifth instruction. And sixth instruction. And now we'll reset. And of course, we need to set all our bus lines back to what they need to be. Okay, so let's see if this works now. Let's just make sure that our instructions didn't get corrupted again. Yeah, looks like we're fine. Okay. Zoom out a little bit so we can see all the registers. Okay. So loading me at 0. That looks like it went through fine. And we're storing into address 15. That looks like it did fine. And now we are loading from address 15. And that looks like it did fine. And now we are adding immediate value of 1. Okay, yep, that worked fine. Now we're storing into RAM location 15. And that looks like it went fine. And now we're jumping back to address 2. That looks like it maybe went fine. Yeah, that worked. Okay, well, let's just zoom back in on our programming interface. And if all went well, if we just click the clock a bunch of times, we should see the, yeah, we're at 2, 3, 4, 5. Yeah, so that's working just fine. Awesome. Okay, well, that took a lot longer than I thought it would, honestly. Yeah, that took a lot longer than I thought it would. But yeah, I think, now have a working Ben-Eater computer made completely out of NAND gates. I was hoping on this stream to get Ben-Eater's Fibonacci program running on this computer by the end, but it's getting to be my lunchtime. So I think I'll wait for a future date to do that. I might set up another stream, like maybe in a week or two or something, so that we can go ahead and do that. Hopefully that one won't be quite as long as this one, but yeah, that's exciting. We got it to work. Yeah, if you guys are interested in this kind of stuff, like this live stream content, more unscripted stuff, go ahead and let me know in the comments. This stream should be available to go back and watch later. So if you want to go back and review it, maybe you missed something, or maybe you just want to leave it playing in the background. I don't know. People like to do weird stuff sometimes, but yeah, it should be available to watch later. And if you are interested in this kind of stuff, go ahead and let me know. Thanks for joining me. I'll see you guys later. Well, no.